So usually in your IR spectrum, if you see a large peak at around 1715, this is a really good indicator that you have a carbonyl group, which is this molecule right here. And so having this molecule, you'll be able to identify what kind of functional group you have. And in many cases, at 1715, it can either be just a carbonyl group, as seen here, or it can be an aldehyde, which is an H, or a carboxylic acid, which is an OH. And all these three are at 1715. However, some factors can affect whether or not it will actually be at 1715. One factor is having a double bond. So if there's a double bond one carbon away from that carbonyl group, say right here, so it's one carbon bond away, so there'd be a double bond, single bond, and then a double bond. This is where you would subtract 30. So instead of 1715, it'll be 1715 subtracted by 30, which should give you 1685. And the range might be somewhere from like 1680 to like 1690, which isn't a problem. Anywhere around 1685 range. And so that's the effect of a double bond. And the effect of a nitrogen is essentially the same, where you'll have a carbonyl group, and then it'll be attached to an amine. Sorry, this would be an amide since it's attached to an O. And the effect is the same. So the base is 1715 of the carbonyl group, and then you'd subtract 30, which would give you 1685 as well. However, if there's an oxygen attached to form an ester, then you would add 30 to the base of 1715, which would give you 1745. Around 1745. So it's essentially the same. It's a range. As long as you're within 5 to 10, it should be fine. And so when I was starting, I was pretty confused between a carboxylic acid and this ester group, because both of them had O's. However, you have to recognize that one is an carboxylic acid and the other is an ester. And if it's an ester, it adds 30 to the group. And finally, the ring structure. If the carbonyl is directly on a ring, that would influence the value as well. So the base is 1715 right here. Sorry, 1715. And so if you lose a ring member, if you lose a carbon and make it a cyclopentane with a carbonyl group on top, you would essentially be adding 30 for each carbon that you were missing, starting from 6. So if you had a 6-member ring and you subtracted 1 to get a 5-member ring, you'd add 30. If you had a 4-member ring, you'd be subtracting 2 carbons, so you'd have 4, which would be plus another 30. And so you'd have a total of 1775 if it was a 4-membered ring with a carbonyl. And so one thing that you have to be careful with, that one I struggled with when I was starting out, was having a member, let me clear up some space, is that if there is a normal 6-membered ring, however, if there's a double bond right here, you have to notice that this is double, single, double, which is conjugated. So you'd subtract 30. So instead of being 1715, it'd be 1715 minus 30, giving you 1685. And so this would apply to all types of rings. If it was a 4-membered ring, you would have 1 and 2 right here. So this would be initially 1715, and then you would have lost 2 carbons, so you'd add 30 and plus 30 for each carbon lost, and then subtract 30 because of the conjugation of the double single double bond. So these two will cancel out, leaving you at 1745. And one more thing that I want to mention was that if it was a carbonyl group attached to a halogen, so in this case an X could be fluorine, chlorine, bromine, this is a special case where it's at 1805 instead of the regular 1715. And so another special case that I wanted to mention was the anhydride. So an anhydride looks like this with the C, O, C, double bond O, and methyl group. So this, if it shows up on the IR spectrum, it has to show up on both 1825 and 1765. And yeah, that's it.